On 30A, it says find the numbers at which f is discontinuous. At which of these numbers is f continuous from the right, from the left, or neither? Sketch the graph. So what do you have to do first if you're going to do 38? What should you do first?
Sketch the graph.
Yeah, actually sketch the graph. Actually sketch the graph, sure. So you have x plus 1. So let's say 1 is right there. X plus 1. X is greater than, so the graph looks, well, I'll use a different color.
Less than.
I understand what it says. I'm doing both directions. So if this, there's the graph, but you want it less than or equal to 1, so what do? Drop everything away except from here on, right? And it's closed dot. 1 over x, or x is between 1 and 3. When x is 1, if x was 1 in there, what would it be? 1. So it's strictly greater than. Let's change this. So this will be blue. So it's going to be right there. And what does it do? What kind of, is it a curve? Is it a line? Yeah, it kind of goes down, right? Gets down smaller, right? And it doesn't contain 3. And then the square root of x minus 3. So when x is 3, what is that? If I plug, yeah, if I plug 3 into here, you get what?
0.
0, that's correct. And it kind of, what kind of arc does it make? Use your hand. Yeah, there you go. I like that. Good. And it does contain that, so this thing goes up and it goes like that. Is that what you got?
Mm-hmm.
Okay, so where does the limit not exist?
1 and 3.
1 and 3 what? Ponies? Yeah, when x equals 1 or x equals 3. You need to say x equals. You can't just say 1 or 3. You need to give it a specific. Okay, so then it asks, at which of these numbers is f continuous from the left, from the right, or neither? So yeah, x equals 1. We'll do left, right, and x equals 3, left and right. So a little grid right here. So what about x equals 1? Is it continuous from the left?
Yes.
It is. What about from the right?
No.
Why not?
Because it's an open dash.
Can you do an interval between them, or no?
An interval between what?
X equals 1 and x.
Yeah.
48. 48?
Yeah.
Use the intermediate value theorem. Nice. Well, remember what the intermediate value theorem is, right? If you don't, what can you do? Yeah, look it up. Use the intermediate value theorem to show that there is a root of the given equation in the specified interval. What does a root mean? What's root mean? What does it mean by root?
0.
Yeah, it's 0. Exactly, right. So you're looking at the cube root of x equals 1 minus x. And you're looking at for the interval from?
0 to 1.
So in this case, it's going to be a solution to the equation below. So how are you going to prove that there is a solution to that equation using the intermediate value theorem? What do you think?
Kind of evaluate it at the ends of the interval. And if it's
Well, what are you evaluating? This is key. What are you going to evaluate?
0 and 1.
But you have two sides. This is an equation. This isn't a function.
You balance the equation by moving.
Yes, you can plug in 0. If you plug in 0,
0 equals 1.
Are you going to solve it for x?
So the intermediate value theorem. Let's look at what page is the intermediate value theorem on. I think it's on. Let's find it here. Where is it? Intermediate value theorem. Can someone find it for me, please? Right there, 131. Page 131 says that suppose that f is continuous. It only works on one function. So what should we do to this?
Make it 1.
Yeah, move everything, exactly. So you're going to end up with x plus the cube root of x minus 1 is equal to, let's call this function g of x. Let's call this g of x. So a solution to this function, a solution is something that makes this equal to 0. Is this a continuous function? Why?
Because it's a polynomial.
It is a polynomial?
No, because
Well, x is continuous.
Yeah.
1 is continuous.
And root of x is 1.
That's right. And cube root of x is continuous. It's in all of those things are in the list. Yes, on the domain, on their domain. Yes, correct. So therefore, the sum of all of them is continuous. So, well, actually, I don't need to say it again because it's already said. So you know g of x is continuous. Okay. What's g of 0? What? Negative 1. What's g of 1? 1. So there exists, that's what that backwards E means. I'll write it out in full English first. So there exists, so by the intermediate value theorem right here, there exists a C value in the interval 0 to 1. That's an interval, not a point, remember. In interval 0 to 1, such that, what? F of C must equal what? 0. We know at some point it's below the x-axis, and later it's above the x-axis. So therefore, somewhere between 0 and 1, what has to be true?
It has to cross the axis.
Exactly. There has to be an x value that when you evaluate it equals 0. So by the there exists a C value between 0 and 1. So what did we just prove what we wanted? We wanted to show that there is a root. So is there a root?
Yes.
Yes. So we are done. So done. There is at least, now this is important, at least one root between 0 and 1. So let's look at one of the other ones here. Which one do you want to do? 50? Sure. So ln x, so it's, this is number 50. ln x equals e to the negative x. And is it 1 to 2? Is that what it says? Yep. So what do we need to do first? We want to show that there exists at least one solution to this. So what should we do first?
You have to set it equal to 0.
Yeah, set it equal to 0. So we have ln x minus e to the
Negative x.
equals 0. And we'll call that g of x. So g of x is ln x minus e to the... So what do we do now? Yeah, g of 1 is going to be ln of 1 minus e to the negative 1. What's ln 1? What's ln 1?
E.
What is the natural log of 1?
0.
0. Minus 1 over e. Is that going to be positive or negative? It's going to be negative. What about g of 2? ln 2 minus e to the... What's that going to be? What's ln 2?
0.69.
What is it?
0.69.
You kind of need your calculator for this, right? It's like
You have to use it all the
0.693
time.
minus
You
1
can.
over e squared. 1 over e squared is about like 1 over 8-ish, right? So if you do this, is that going to be positive or negative? Yeah, you need your calculator a little bit. You can use some logic. You know that you just basically need to know that what power of e equals 2 is going to be greater than 1 over e squared. So it's positive. So what do we now know? There exists a c value contained in 1 to 2 such that, that's what that bar means, such that what? Oh, not f, what is it? What did we call the function? Such that g of c is equal to 0. So there exists at least one solution. I'll write this out for you. That means there exists contained in, and that bar means such that. Does this make sense, everybody?
Yep.
And this only works, actually, there was one thing we needed to do before we use the intermediate value theorem. What's the one thing you need to know about the function in order to use the intermediate value theorem? Yeah, it's continuous. Well, we know that this is continuous, and this is continuous. So, g of x is continuous. That's correct. Correct. Okay. Any others? Any others you want to talk about? And finding a solution to this equation is the same thing as finding a root to what? x. We just did it twice up here, kids. I'm not asking you to invent any new system here. Finding a solution to this is the same thing as finding a root to. No, what function specifically?
X cubed minus x plus 1.
X cubed minus x plus 1. Yeah, put the x on the other side. Absolutely. Exactly. So, did they give us an interval?
Nope.
So, what do we get to pick?
Make one up.
Make one up. Okay, so how about, what do we want to do? G of what? G of what? 1? What's G of 1? That's going to be 1 minus 1 plus 1. What's that?
1.
1. Okay, that's our positive one, so we need to find a negative one. So what should we pick? G of what? Negative 2. That's going to be negative 8 minus negative 2 plus 1. What's that going to be? Negative 5. So you know it. G of x changes from negative to positive on the interval. What? No. Negative 2 to what? 1. The interval's from negative 2 to 1. And it changes from negative to positive how many times? Yeah, so how many times? It doesn't have to be infinitely. It's at least how many times?
At least once.
At least once. What else do we need to know about this function? We know g of x is what?
Continuous.
Why? Yeah, but what kind of function is it?
Polynomial.
Yes. Exactly. We know it's a polynomial, so it's continuous. We know it goes from negative to positive. Therefore, by the intermediate value theorem, there's a c value contained in what? What's the interval? Negative 2, 1, such that, not f, I keep on writing f, g of c is equal to 0. So, there exists at least one what? One solution.
Yes.
But you have to show it's continuous on the closed interval. And if the function is continuous everywhere, is it continuous on any interval? Jackie, stand up. Record. Okay. So it says use the squeeze theorem. We already talked about the squeeze theorem, didn't we?
Yes, but
We talked about the squeeze theorem, didn't we?
Yeah.
In this class, have we talked about the squeeze
Yes,
theorem?
we
Yes or
have.
no?
Yes.
Good.
you grabbed it.
Thank you.
Doesn't calculate.
Use the squeeze theorem. Okay. So let's talk about this for a second here. Sine x has to be less than or equal to what?
1.
Greater than or equal to?
Negative 1.
Divide everything by x. Negative 1 over x has to be less than or equal to sine of x over x, which has to be less than or equal to
1
1 over x.
1 over x. What's the limit as x goes to infinity of negative 1 over x? 0. 0. Negative 1 over something the size of the Exxon Valdez is really, 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 really small. What's the limit as x goes to infinity of 1 over x? 0. Therefore, by squeeze,
We're dumb.
the limit as x goes to infinity of sine x over x is 0. Yes. This function is squeezed between these two.
And we can just use the results.
Yeah. You just have to show, what's the key to using the squeeze theorem? You have to show this right here. You have to build something that's definitely true, that it's always between, yes. Use the graph of f of x equals sine x over x. How many times does the graph cross the asymptote? So did you graph this?
Yeah.
A lot.
What happens to this graph as you go infinitely to the right? So the bounds are there, right? Here are the bounds, right? Do you agree with that? Yeah, the bounds are there. That's great. So it does stay in between them. But what does this function do as it goes on? It goes. So how many times does it cross?
All of them.
Crosses all of them. Yeah, crosses y equals 0 infinite number of times. Does that make sense, everybody? Yeah. It's going to keep on oscillating. It's going to get smaller, but it's going to keep on oscillating. Why does it get bigger here? You're dividing by a dividing by a fraction eventually. So, yeah. Okay, moving on. What's the degree of the bottom? What's the degree of the denominator? 3. The degree of the denominator is 3. What's the quote unquote degree of the numerator? What's it about?
3.
About 3. So do you suspect that this has a horizontal asymptote, something, a limit that isn't 0?
Yeah.
Yeah, you suspect it has a limit that isn't 0. Suspect. You could graph it, and it definitely shows up as not being 0, right?
Yeah.
You go really far out and it gets really close to, looks like it's really close to 3, right? So we have to prove that. So we have to do some clever manipulations to this. What are we going to divide by? Someone raise their hand and tell me.
Wait, didn't you just...
If you tell me that that's 3x cubed minus 1, I'm going to be very sad.
No, but can it be 3x cubed minus root x?
No.
Oh, no.
What happened to the raptor?
It has laryngitis and it's spiraling the drain here. What are we going to divide by? Give you a hint. I want to divide by that on the bottom. What am I?
1 over x cubed.
Close. Not 1 over x cubed. What am I going to divide by? The square root of x to the 6th. That is just, we did this yesterday, didn't we? This is just a fancy what? Fancy form of what? Yeah.
Just pulling numbers out of nowhere.
Well, it's not nowhere because this is cubed, right?
Yeah.
So if you're multiplying by 1, it has to be the same on the top and the bottom.
Yeah.
But yes, it's new to you, so it takes a little longer. So what does this become? It becomes the cube root of 9x, well, the square root minus over this, all over what? X cubed plus 1 over x cubed.
I
What
have
does
a
that simplify to?
question.
Yeah, sure, Hutch.
You are multiplying, not dividing, yes?
Oh, sure. Yeah, sorry.
Okay.
Yes, I'm multiplying. Yes, absolutely. Sorry. I could have taken out the compound fractions and made it divide. So, yes, absolutely correct. So, what does the bottom simplify to? What's the denominator simplify to? 1 plus 1 over. Right? What about the top? The square root of what? 9x6 minus x over x to the 6th. So what does the top simplify to? Minus 1 over what? 5th. Over 1 plus 1 over x cubed. So now if you add in the limit as x goes to infinity, if you add that in, what does this go to? What does this go to? 0. So what does this whole thing equal? Square root of 9 over 1, which is 3. You just did it there. Yay! Does that match your graph? It should.
Yes.
If you type it incorrectly, it should get really close to 3.
Wait, I know.
Yes. Yes, what? What?
What's the step from the first one that you did in black to the second one?
From here to here?
Yeah.
Well, 9x to the 6th over x to the 6th is equal to 9. Negative x over x to the 6th is equal to 1 over x to the 5th. Yeah, that's the step. Does that make sense? What do we want to call this kind of manipulation? Magical root division? Want to call it that? Is that good? Magical root division.
You were teaching us magic.
Magic! Woo! Magic! 请坐. Okay, we good? We like that one? Let's pick one more from this page. What do you think? One more.
12.
12?
I don't know.
We're going back? We're going retro. 12. Evaluate the limit, right? Oh, come on. You can evaluate the limit. You don't even have to do anything fancy on this. Nothing fancy. They want you to justify each step, meaning they want you to use the limit laws. Okay, so what can you do with a radical?
Just take that and put it over the entire.
Exactly. So this is the same thing as the limit of this. Over 3x cubed plus. Correct? Right. Exactly. So now we find the limit and then we just square root it. We find the limit and we just square root it. Exactly. So what's that going to be? Well, I understand. We need. What are there any logical steps we need to show first? Well, yes. You can. At this point, I would if you were going to explain this, all I would need you to say is you can bring the root out. But now when you do this, what's this going to be approximating? So this limit, you could say it looks like this. You could say it's the square root of the limit as x goes to infinity of what? What are the only terms that matter?
The 2 and the 1.
12 and 3x cubed. So what happens? That's gone. This is the square root of the limit as x goes to infinity of 4, which is the square root of 4, which is the principal root, which is 2. Yes.
Well,
Yeah.
the square root of 12 over the square root of 3 equal to 2?
Yes, because 12 over 3 is 4.
4 and
Yeah.
4.
It is.
Okay.
Wow. Another way to show that, if you really care, look, you're talking about this. You did this separately, right?
Yeah.
Well, that's equal to the square root of 4 times the square root of 3 over the square root of 3, which is the square root of 4, which is 2.
Boom.
We good? Any last questions you wanted to ask about? Any last questions that you were like, oh man, I really need to ask about this? Okay, put it all away, please. Keep out a pencil. That's it. If a curve C has an equation y equals f of x, okay, nothing new there. And we want to find the tangent line to C at a point a f of a. So the x value is a, and the y value is going to be
F of A.
f of a. Then we consider a nearby point x f of x, where x is not equal to a. Compute the slope of the secant line. The secant line is just the line between any 2 points, right? So we have this curve C. It's going to be y equals f of x. And we have a point P, and that's a comma f of a. Then we have another point x comma f of x. So if we want to estimate, we did this before, if we want to estimate this slope right here, maybe it's not quite like that, but let's say we want to estimate that slope right there, and I'm still doing a terrible job of drawing tangent lines, but that's okay. How did we estimate it? Well, we took the slope of this secant line right here as an estimate. It's not going to be super accurate for this picture, but is it more accurate than a random guess?
Yeah.
It's more accurate than a random guess. So this is the notation here. If you wanted to find the slope between those 2 points, the rise is going to be, does it matter what order I subtract them in?
No.
As long as it's what?
Same.
Consistent. Exactly. As long as it's consistent. Could I switch x, just the bottom here, x and a?
No.
No. So the slope, this is q, the slope from p to q is that right there. Are we okay? Yeah. Now if we want to make this more accurate, if we're anchoring point P, if we take that and we put a tack right through it, what could we change? Point Q. Yeah, we could take Q and march Q closer and closer and closer. Becomes more and more accurate. Now we did this with tabular sets of data where we had some sort of like trajectory for the numbers and we made our best guess. Why isn't that always, is that always going to work?
No.
No, it's not always going to work. Can it lie to you pretty easily?
Yeah.
Yeah, absolutely. Okay, so we're going to use a precise definition now. The tangent line to the curve y equals f of x at the point P, a f of a, is the line through P with that slope. What's the one thing that we just added in here? We added in the idea of a limit, provided that the limit exists. Provided that the limit exists. Do we have some tools that we can use to evaluate limits?
Yes.
Yes, we have some tools. We don't have too many tools, but we have some. So let's try an example. Let's do our first. Well, we've already done it kind of, but let's apply this directly to a parabola. So we have that parabola right there. And we want to find the slope of the tangent line at the point 2, 1. Assume I'm not lying to you. 2, 1, is it on there? If you plug in 2, do you get out 1?
Yeah.
Yeah.
Yeah, you do. Okay, so we're going to evaluate this limit. The limit as x goes to what x value? What's the x value that we're approaching? 2 of, I'm going to write this out, f of x minus a is f of 2 all over x minus what?
2.
2, yes. What is f of 2?
1.
Yeah, it kind of gives it to you in this. X goes to 2 of f of x minus 1 all over x minus 2. Are we good so far?
Yep.
Do we know what f of x is?
No.
Yeah, we do. It's that function right there.
Oh.
Sorry. All I'm doing right now is rewriting what we have so far. That is the function we're operating on. So we have the limit as x goes to 2 of 2x squared minus 5x plus 3 all over, oh, minus what? 1 all over x minus 2. Are we okay so far?
Mm-hmm.
What do we think? We okay? Let's simplify this a little bit. What can we combine? What's the one thing we can do to the top?
You can subtract 1 from 3.
Yes. Very good. Over what? X minus 2. Okay, it's a rational function. We want to find a limit. What's the one thing that we could try at this point?
Plug in the
Factor.
number.
We could try plugging in the number. Can we plug in 2?
Nope.
No, can't plug it in. Always check that first. That's great. Thank you for the reminder. Next, we should try what?
Factoring.
Factoring. Can we factor the numerator? What do you think? Hopefully, what would be really nice if we could factor out of the
X
numerator? Okay, so key things here. What does this have? You've seen this before. You first saw this in Algebra 2. What is that?
Slope.
That's just finding the slope between 2 points. And we're just doing something kind of fancy. We're fixing A, and what are we changing? X. X is on a journey towards what?
A.
A. That's all we did. We fixed it. That's it. That's completely it. We anchored that point, and we took this blue dot, and this blue dot is on a journey, right? Yay. So we called that x comma f of x, and we called this a comma f of a. Exactly. Another way to think of this, instead of thinking of it as 2 separate points when one is fixed, you're gonna fix this. Let's say we'll fix this point right here, and instead of moving this point by changing x and f of x, we're gonna think of it as centering our motion around the distance between the two. From here, this distance right here, we're gonna call this h. As x gets closer to a, what happens to h?
Approaches 0.
H approaches 0, right? So instead of writing this x f of x, we could write this as, and could h be negative?
Yes.
Yeah, h. We could go in backwards. Okay, I'm gonna write. If I write plus h, is it okay if it goes left?
Yes.
So instead of this, what's the x coordinate for this point right here in terms of a and h? Yeah, but if h is negative, what would it be?
Plus A?
Yeah, let's say a plus h. And what's the y value? F of.
A plus H.
And in this case, h is going to go to what instead?
0.
H is going to 0 instead. All we're doing is we're writing the limit a different way. That's all we're doing. So in this case, we're looking at the limit as h goes to 0 of what? F of a plus h minus f of a all over what? What's the denominator going to be?
F of A plus H. Well, it's H. Because it's F.
What is it?
A plus H minus A.
It's a plus h what?
Minus A.
Minus a. Exactly. So what does this become? The limit as h goes to 0 of f of a plus h minus f of a all over h. This is 2 ways to write the exact same thing. 2 ways to write the exact same thing. Sometimes you're going to be pushed towards using this definition right here, and sometimes you're going to be pushed to using this. Is it the exact same thing?
Yes.
The only substitution you made was x is equal to a plus h. That's the substitution you made. It simplifies to the exact same thing. Are we okay with that?
Yeah.
It's really important you see this because the book will sometimes change between the two and it'll look like they're doing something fancy. Are they doing something fancy?
No.
No. You're multiplying by a form of 1 at this point. We can't plug in 3. So what are we going to multiply by?
X plus 3 over X plus 3.
That's a great suggestion. It's even simpler than that. I don't like fractions. What can we multiply the top and bottom by to get rid of all the fractions? What's the only denominator in the numerator? What happens if we multiply by that? What do you get? You get the limit as x goes to 3 of what? Minus all over minus 3x. Huh. Can we plug in 3?
Yes. No.
No.
Not yet.
We can factor.
What can we factor now?
X. And then cancel it.
Let's see if it cancels. We get x over what? X times what?
1 minus 3.
X minus what?
3.
Is that really close to what you want?
Yeah.
What could you factor out of the numerator to make it exactly what you wanted?
-1.
-1. Thank you. So many kids just don't like factoring out -1 for some reason. I don't know why. So what is this going to become? The limit as x goes to 3 of negative what?
1 over X.
Well, let's do the intermediary step. Negative x minus 3 over x times x minus 3. What cancels?
The X minus 3.
Pretty cool, huh?
Yeah.
So you're left with the limit as x goes to 3 of -1 over
3.
x. So what's it going to be?
So,
Negative what? 1/3. So this is less calculus and more what? Algebra. The calculus you have to use to set it up, and then you should crush it with your awesome algebra skills. The big takeaway from this, are there two ways to write the same type of limit for slopes of tangent lines?
Yeah.
Yes, absolutely. Same type.